Brad McCredie will be giving our next talk. So Brad is the Corporate VP of GPU Platforms at AMD. He joined AMD in 2019, where he's the Corporate Vice President of Data Center GPUs and Accelerated Processing. He was with IBM since 1991 before he joined there, so he was a fellow there. Brad oversees the global development, delivery of sales and data and GPU products. And with that, let's please keep it down. So with that, Brad, it's all yours.
Oh, thank you. Just do a quick check. Somebody can wave if you guys can hear me okay? Yeah, lots of waves. All right, I'm waving back. There we go. All right. Well, thank you very much, and I appreciate Michelle and the organization team for accommodating our AMD policies. And I'm sorry I'm not able to be with you guys there in person. So today I'm going to talk about a talk that is not a complete surprise to anybody. That we all know that our technology is not scaling as fast as it has been in the past. And we need to all keep thinking about what we're going to do in that environment. To that end, I'll put this chart up. I find this chart, it's interesting. It was like a marketing chart, but it's an interesting chart because if you think about what this chart looked like not too long ago and the workloads that would be on this chart that were driving such demand, it would be a very different in nature, which reflects the difference in nature of what computing's doing these days and the economics behind it. For a good hunk of my career, going back to the early 90s of computing, computing was an automation process. And therefore, the value of computing was capped. And what do I mean by that? Is, when a computer is automating something, whether it's payroll, a database, enterprise resource planning, the value that computer can provide to any industry is limited by how much was being spent on that process. Now, if you look at this list and what the computers are being used for, they're a competitive weapon. They're a competitive weapon. It's competitiveness. It's beating your competition. The value of that is much, much more uncapped. And this is what is driving an increase in rate and consumption of computing, and it's also what's driving an increase in rate and investment in it, because the actual economic impact is growing. Now that's all really exciting, but then we follow that up with this chart. There's many, many flavors of this chart floating around these days, but they all say the same thing, which is, that economic fuel that, has driven so many of the, comparisons, that if cars were improving at the rate of computers, cars would be going somewhere in the neighborhood of, 1,000,000 miles an hour and cost 5 cents. This chart pretty clearly says, hey, that great fuel to our industry is drying up. The nodes are spacing out. We got more time between the nodes than we've ever had before. And likewise, the thing that the right side, the normalized cost of a die, it was constant for forever. And, that is now going up. And that, the drivers for that are pretty well documented: multi-layer patterning, deep UV type lithography, and many, many other things driving the cost of the die up. Now, we started out hitting that with a hammer. That's what this chart says here is, we said, okay, fine, if the technology's not going to scale, we know what to do. We're going to go and spend more on cooling. We're going to build bigger die and spend more on transistors. And that's been happening, but also you can see, that playbook isn't going to run too long. There are definite limits to how long you can go and hit the technology with that hammer. If you look right now at power, our most powerful GPUs, and they're carrying a lot of the weight of the computation in the deep HPC space, they're at 300 watts. That's starting to look like some pretty fundamental limits, when you start thinking about air cooling and things like that. Now we could obviously go and hit it with another hammer, liquid cool things, and drive even further up. And that could happen in some spaces, but I don't know if that'll be a broadly adopted solution. The right side, we'll talk a little bit more about it, but we'll have to start breaking the dies up. So if you look at this is kind of a problem statement, and as well as a little bit of a statement what's happening. If you think look in the reverse direction, right? If you look in the reverse direction, most of the value was very much carried by the technology, where we're coming from. You go back into the 90s, even 2000s, early 2000s. Most of the value generation to generation was coming from the technology. It was just a tremendous value generator. But now that's healed off. We got a bit of an increase in the desire for consumption, as I pointed out before. We got workloads that are just driving tons of value in the industry. So desire for consumption has gone up a little bit. Our technology's tailing off. We got a wedge to fill. So let's talk about how we're going to fill that wedge and take a look at a few things here. So this is the list of the candidates to fill the wedge. The first time I gave this type of talk was actually in 2012. And when I talked about this problem and drew the picture of the value wedge, I really looked at the one dimension of what might be the fix to this was really packaging. Now, it was at a keynote at a packaging conference too, so I was probably playing to the audience a bit. But it looked like the biggest gap filler for these problems was going to be the packaging. Now, it's really, really obvious to me, and I think to the whole industry, you got to innovate across the whole stack. We got a big wedge to fill of value. Cost performance needs to be maintained. And I think we're going to be looking across the whole stack to fix this problem. So let's look at microarchitecture. Now this chart, looks like, hey, a chart that we see a lot, but it's actually shifted a lot in meaning as recently as the past 3 to 5 years. Usually we would put a chart up like this and say, okay, the first one on the left was in this technology node, the next one was on the next technology node, and we're going to march through those technology nodes and work our way, forward in time. And that now it's actually kind of different, very, very different, really. It's more like, the technology's not doing a whole lot, and whatever you do, the worst thing that can happen is you can have the technology get away in getting your series of architectures to market. And that's a very, very, very big shift. So, now a lot of times when we used to say, okay, the technology is going to be available on this date, how much function can we pound into a die and be done when that technology is ready? Now we're really saying, okay, how much function do we need to do to have a competitive solution, and what technology would be there? And it shifts things a lot. So designers like me, I actually came from the design side of the house, not the technology side. Who's carrying the mail has shifted a lot in the recent years. Whereas now we used to always, as a designers, would always kind of get in trouble if we held getting the technology to market up, because that was generating the value. Now the technology guys are a little bit more in that hot seat. So it's changed the competitiveness. If you look at let me see, make sure that's not blocking things there. If you look at what's happening in the industry trends and rates, now we're measuring competitiveness on the who's going to go the faster on the design and innovation side, and this is what we measure ourselves to as well. How far ahead of the industry improvement rates are we getting with our designs? Because that's really where the value is being generated from. And so we plot these plots very carefully and measure our competitiveness relative to the rest of the industry. Now the next thing that that really is going to have a big impact if you look at the industry is the packaging technology. If you look at where we're coming from, you know, the picture on the left, as everybody well knows, used to be a single die on a module. If you go back far enough in time, there was lots and lots of dies on a module. That was when we were in different types of technology, such as bipolar. Going forward, we're going to be breaking those dies up more and more. And of course, you know, even more importantly, you know, there will be heterogeneous technologies on those modules. So the high performance pieces and the high performance technology, low performing pieces, and easier to yield, much lower cost technologies. And then the most important thing, of course, as well, is we can get a lot more compute onto a single module. Now, this is probably you know something that can enable self-inflicted wounds as well, because now you got a lot of square millimeters of technology there. Without careful design and practices, you know, you can go and burn lots and lots of watts, as I showed in one of the very first charts. In many cases right now, you know, a lot of dies are up against the reticle limit, as I also showed in one of the earlier charts. So they were driving a lot of packaging innovation to enable us to break the dies up into much smaller pieces as well. And so if you look at that, you know, right now the biggest thing that limits to how small a pieces we can break the dies up into, it's generally driven by how wireable the substrates are on these pictures. So if you look at this chart, you know, that's one of the first things that's filling in the space, you know, of this wedge of needing a TCO improvement. It's going to be, you know, can we get new microarchitecture and packaging technologies to just improve the efficiency and the performance of what we're doing. Okay, so now let's look at heterogeneous architectures. This is probably the biggest hammer that we've been hitting the TCO gap with, and certainly the top 500 list of HPC computing, which I'm sure many people in this room are familiar with. You know, it's the best evidence. You know, we've gone from just the top 10 machines being, you know, a heterogeneous architecture to the point where we're getting to the majority of the machines on the top 500 list are in a heterogeneous architecture. And this is the battle that we're fighting, you know, when it comes to the heterogeneous architectures. We want to try and find, you know, something that can improve performance per watt, performance per square millimeter, basically cost performance as much as possible, but have as wide of a curve as possible on a curve like this, meaning it covers the most applications. It's easy to get, you know, large amplitude, but have a very narrow application coverage in these spaces. If you look at this chart, it can show you how strong that can be. This is comparing a GPU to a CPU, as well as the CPUs going and using the AVX512 or, you know, vector type functions. You can see that versus a base CPU, a GPU can be anywhere from 3 to 5 times more efficient on performance per watt, which is a key metric. Performance per square millimeter, you can get much higher. That's a very first principle capability, because the GPU just doesn't have to carry as much architectural rigor and structure to it, and it enables us to create very dense compute on the GPUs. Even when you go and play where a lot of the CPUs are going, you know, try and put more vector function and capability into it, it isn't a big swinger as far as the performance density and the performance per watt, as you might think. And no matter how you slice it, if you're going to make the investment in programming, you'll want to keep thinking about going to the heterogeneous architecture, because it's the biggest hammer to hit the efficiency with. Now, the other thing you want to do is you want to make make it easy to hit a broad spectrum of workloads. And one of the best things that we've got coming down the pipe right now to make it easier to program, make it easier to hit a broader spectrum of workloads with the GPU. It is really coherency between the CPU and the GPUs. And that's what the infinity here represented on these charts. That's a coherent fabric. It's our particular AMD infinity fabric. Most of the GPUs these days are connected to the CPU, of course, through a PCI bus. But the infinity fabric relieves the programmer from a lot of the burden of having to maintain the system memory in the right spot or keep the right copy of the system memory in the right spot between the CPU and the GPU. And it replaces it with a hardware capability. And that makes a big difference in the amount of code you have to write and the complexity of the code. We did a quick example of a real simple piece of code written. One version on the left here is written just for CPUs. Middle version is a GPU code without coherent memory between the CPU and the GPU. And then the right side is that same code run on a GPU, but assuming that the hardware coherency is in place. You know, while it's not the last answer and the be-all and end-all to fix everything, the coherent fabric between the CPU and the GPU is going a long ways to making writing GPU code look and feel a heck of a lot more like writing for a CPU, as you don't have to do by hand the memory coherency. So that's the next plot here. You can see I put in the heterogeneous architectures. I actually showed the heterogeneous architectures leading the uptick in consumption. And that's kind of just an artistic rendition here of what I think really happened in the industry, which is, if you think about it, right, you know, we had to get the GPU and the capability and the computational capability of the heterogeneous architectures out there in the industry first. Then we really saw the big innovation in the AI and the machine intelligence codes, and then that consumption started to take off. So you can see that, you know, that trend is, you know, represented here on this graph. The last piece that I was going to take a look at here is the open innovation piece. Here on the open innovation side, you know, the real point here is the complexity and the challenges of getting CPUs and GPUs and all of this hardware to go and solve bigger, harder problems at once. If it's done proprietary or on a single platform, you know, no single company has probably got all the tools to do everything that's represented on this page. Give us a nice accelerated programming API, unified tools across CPU and GPUs. There's a ton of work to do with machine learning optimizations. Make that code portable across platforms and give a broad ecosystem for it. That's a really, really, really tall order for any given or single company. And I don't think that can be done by any single company, even the largest ones out there. And so we really believe that this needs to be done on an open platform so we can bring everybody to bear onto the same platform and do the innovation that is needed to move the state of the art forward. And so if you look at what we're doing, we're trying to make this an entirely open stack across tools, frameworks, libraries, and compilers to enable everyone to bring to bear the innovation to one spot. I think that's going to be important. There's a lot of moves in the industry to try and create this capability and bring it to bear. I think this is going a long ways to what we're doing here at AMD to be able to enable this all with an open framework and an open libraries, open compilers, open tools is an important thing for everyone. The one point, though, that I would bring out also is that not only is open really important, enabling everybody to get onto the same platform, the other thing that is very important is to get a cross or multi-platform capability. And one of the things that we're also doing is we're enabling everybody to bring CUDA-based applications into a single resulting C++ code. We call it portable HIP. to enable that to be compiled onto both AMD and NVIDIA GPUs. I think this is really important as well for the industry, as we're looking for a single place to innovate that can be run across a broad spectrum of hardware. And this capability enabling CUDA-based applications, which there's a lot of the CUDA code out there, to be able to go across a broad range of GPUs will go a long ways towards being able to make that happen as well. The HIPify step, goes through and does the modifications of the CUDA code in an automatic fashion into the portable HIP code. All right, last point. So that fills in the last gap. Nothing too exciting there. Moving on then to just a wrap-up point here as we bring this point together. The hardest thing is going to be bringing all of this innovation to a single spot across CPUs, GPUs, and the open software stack. And that's going to be probably the biggest way we'll be able to drive this innovation in the industry and go where the industry is heading. And I like to point out that we're able to bring all of these pieces there to the platform, both the CPU, the GPU, and the open software stack. And I think that'll help drive the innovation of the whole industry forward faster as we go and try and leverage these architectures. So with that, I'll take a breath and take questions as they come up and engage anything we need to talk about.
Let's thank our speaker. We have time for a couple of questions. Super important that you might wait for the microphone. You can hear us, Brad?
I can hear you just fine.
Okay.
Thanks.
So any questions? While they're all priming their questions, so you talked about the width of that curve on the application space, How much of that is really driven by Amdahl's law, and how much is programming models and compilers and that technology, you think, that how much can we broaden that and keep the elevation, if you will, of the peak? Or is the area under the curve going to naturally just have to be fixed?
Actually, it was kind of the last chart that I showed is that there is obviously, it's a great question. There is obviously a big piece of that can be driven by Amdahl's law, which is it's a good way to bring out the point on the last chart, maybe even better than I did in my discussion, which is, you're gonna have to have the CPU and the GPU work together. I talked about the coherency, for example, between the CPU and the GPU in the context of ease of programming, but that's also driving area underneath the curve, right? Because you're gonna want to put a really, really strong thread on the CPU to handle those inevitably serial portions of the code, and then you're going to want to have your fire-breathing, big honking GPU being able to handle the parallel pieces, and so the co-innovation, the co-development of both the hardware and the software is what drives area under the curve. Now is it a 50-50 proposition, or is the bulk of it on the software side? Actually, I would say that the true area under the curve is going to be driven by the hardware. We're going to have co-optimization to get the area under the curve there. To get people to use it and really get the TCO down, to be software limited.
Okay, thank you. We have a question here. John Malacrummy asking a question.
Brad, this is John Malacrummy from RES. So you talked about the coherent fabric as being sort of a key part of making it easier to program. Do you have any experience that shows that this leads to programs with good performance? What I've been hearing is that actually using this unified memory model is actually not yielding nearly as good performance as managing it manually.
So the answer is yes. I can cite both FPGA and GPU examples where the coherency has driven good performance. Part B of that is, in all candor, do we still have to tune some things? Yes. No, we did. But it's one of those things that I can just guarantee you, given my experiences, that it will get better with time. It will get better with time. You know, we're still in the infancy stage of doing the hardware-based coherency. You know, it's probably not as optimal, and the libraries aren't as optimal as we would like them to be. But I'll also guarantee you that, you know, with time and use and tuning, they'll get better over time as well.
You have one question in the middle here? We're waiting for the microphone. It's coming.
Hi, Brad. Addison Snell, Intersect 360 Research. I have a question for you not to answer. We've noticed that your Raven Ridge product with Ryzen offers shared memory between the CPU and GPU. Any chance that we'll be bringing that capability with Infinity Fabric onto the server side? Shared memory between EPYC and the GPU.
Yeah, we will be bring that is coming. Well, we talked about it publicly that in next generation we will have coherent fabrics between the CPU and the GPU and AMD products.
Any additional questions? If not, let's thank Brad again. Thank you, Brad. And look forward to catching up with you next time in person.
All right, thank you. Thanks for your accommodation again.
Yeah,
Appreciate it.
Thank you.